Compilers are how we take the code you write in languages like C and C++ and turn them into machine code, which is like the ones and zeros your computer can actually understand. And they consist of five main crucial steps, which are the lexicon analysis, syntax analysis, semantic analysis, then code optimization, and then finally generation, the ones and zeros that your computer actually understands. My name is Adi. I'm a software engineer at Amazon, and in this video, I'm going to explain how do compilers actually work in a way that I wish it was explained to me. So we're going to first start with lexical analysis, which is think of it like this is where your code first arrives. The lexer, which is short for lexical analysis, is like the first inspector who checks every part coming off the truck. It looks at your code character by character and groups them into meaningful chunks called tokens. When you write int x equals 42, the lexer breaks this into tokens. Int, which is a keyword, x, which is an identifier or a variable, equals, which is an operator, 42, which is a number, and then the semicolon at the end, which is punctuation. It's literally reading your code like you read a sentence, identifying nouns, verbs, and punctuation. And if you have a typo like instead of int, you have 1nt somehow, this station catches it immediately because 1nt isn't a valid token, just like a factory inspector would reject a warped metal sheet. Next, you have your syntax analysis, which is basically going to be like the parser now takes those tokens and figures out what you're trying to build. It's like taking all the car parts and checking them against the blueprint to understand, oh, these four pieces form a door. The parser builds something called an abstract syntax tree, basically a diagram showing how your code fits together. When you write x equals a plus b times c, the parser knows multiplication happens before addition. Remember like order of operations from like math class like PEMDAS, that's essentially what your compiler is figuring out. And so it builds a tree structure reflecting that. The GCC compiler and Clang both do this, but Clang is known for giving way better error messages at this stage, like a helpful foreman at the factory who explains exactly why your blueprint doesn't work, instead of just saying, nope, we're not doing this. Next, you have semantic analysis, which essentially takes the language you're working with and that abstract syntax tree that you created earlier. It makes sure that the code that you've written follow all the rules of your programming language. Like you use the right types, you used the right flow of that language. And so it's going to take that tree you created and it's going to verify every single thing. It's also going to have a much deeper understanding of how your code base is interacting with one another. So it's going to see all the dependencies that are moving around your code base, between different files and functions. How do they all work together? And it's just going to make sure that everything makes sense for your programming language. So at this point, your code is compilable. It can turn into ones and zeros. But a compiler does a great job of optimization. And so this is where things start to get really interesting. Your code works, but you can make the final product faster or smaller, which means less instructions for the same output, which means faster. And the optimizer is like an efficiency expert walking the assembly line. If you write x equals 5 and then y equals x plus 0, the optimizer realizes adding 0 is pointless and just makes it y equals 5. This is where you see the big trade-offs. GCC has optimization levels from 0, which is no optimization, but compiles quickly, to 3, which is aggressive optimization, but compiles slower, but runs far faster. Google's engineers found that version, the second version, instead of 3, on Chrome, saved 5 to 10% in binary size with barely noticeable performance differences. Now, Rust's compiler, which is a very famous language, at least in the recent years, is famous for really aggressive optimization by default, which is why Rust programs often match or beat C++ in speed, but compilation takes forever. A medium Rust project could take somewhere 2 to 3 minutes to compile versus 30 seconds for an equivalent sized C++ project. And lastly, you have like the final assembly of this like car we've been talking about, or code generation, the binary that's actually being created. And this is where like your actual machine code is created, the ones and zeros. And this is like the final part of your assembly line. And different chips have different instruction sets. And so there's going to be like RISC instruction sets or CISC instruction sets. And they're going to be different based on like an Intel x86 chip versus an ARM processor, which is like in your iPhone or Android phone, or like the Apple MacBook chips have Apple M1. And so like the LLVM compiler used by Clang, Rust, and Swift, is going to be basically a universal backend here. So it's going to be assembling cars for different markets, or assembling your code into the ones and zeros and like converting the instructions into the ones and zeros based on every type of CPU out there. Or if you're using an older compiler, it's going to be using, is going to be very dependent on the CPU you actually compile it onto. And so, what you're going to have basically here is 10 to 100 times faster software compared to interpreted languages, which we'll cover in another video. And but this, like the big problem with compiled languages and compilers is that you can't just start executing your code right away. You have to solve most of the bugs up front, which is great for enterprise use cases where you don't want your code to break 3 hours after launching, after like a few people have already started using it, which could be like very big clients or merchants. And you rather take a little longer when developing code, but ensure that you don't have a lot bigger problems later down the road. And that's all there is really to a compiler.